everyone, this is Mrs. Backlund. I will apologize first because I know there's kind of a staticky sound and it's pretty annoying, but I'll do my best. Today we're learning about polynomial and synthetic division, which is actually something that you did learn in Algebra 2. We'll do both long division and synthetic division, and hopefully by the end you'll sort of see how everything comes together as far as zeros and factors and divisions and all of this. And just up here I put an example of a long division problem and an example of a synthetic division problem, and that's what our goal is, to be able to do that and then know what it means. We're going to start with a long division problem, and I have the technical names written here. This is the dividend, here's the divisor, our answer will be the quotient, we might wind up with a remainder, but mostly I just care that you can do this technique, not the vocab so much. So we've got this big old polynomial divided by this other polynomial of degree 2. So we're going to take a 4th degree polynomial divided by a 2nd degree and see what we get. So, step 1. We want to put something up here so that this term times the x squared will give us a 6x to the 4th. And so that's why I'm going to choose a 6x squared, because 6x squared times x squared makes 6x to the 4th. That was kind of the whole goal. But we're actually going to take the 6x squared and distribute it through the entire divisor. So just imagine that we're distributing, and then putting what we get right here. So I'll take 6x squared times x squared, and then I'll continue. 6x squared times positive x is positive 6x cubed. And then finally, 6x squared times negative 1 is negative 6x squared. And I'm sort of trying to keep these degrees lined up, so if we have a 4th power, a 3rd power, a 2nd power, leave them lined up. And then every time we get to this step, we subtract, just like our old long division that we learned in elementary school. So we'll do 6x to the 4th minus 6x to the 4th, which is nothing by design. That's how we wanted it. Now this, you have to pay attention because we're subtracting each time. Some people like to distribute that so they don't get confused, but we're subtracting. So negative 1x to the 3rd minus 6x to the 3rd is negative 7x to the 3rd. And then we'll do another subtraction, negative 1 minus negative 6, and I think that's a positive 5x squared. And then you can go ahead and drop down whatever's left, the plus 9x and minus 3. Now we're going to repeat. I'll switch colors just for fun. So now I'm going to go back up to the top here, and again I'm looking for something times my x squared that will give me that negative 7x cubed. I believe I'm going to go with a negative 7x, because negative 7x times x squared is negative 7x cubed. And negative 7x times x will give me negative 7x squared, and negative 7x times negative 1 plus 7x. And every time I subtract. So, negative 7 minus negative 7 is no x cubes. 5 minus negative 7 is 12x squareds. 9x minus 7x, 2x. And, well, negative 3 minus nothing constant is negative 3. That's why those drop down, because we're not really subtracting anything from them. I think we're on our last step. Are you seeing it? So last step, I'm looking for something in my quotient so that that times x squared will give me 12x squared, and it's got to be 12, right? So I'll take 12 times all three of these things, just distributing it through. 12 times x squared. 12 times the x. 12 times the negative 1. And I think I get, oh, remember we're subtracting. Subtract. And I get no x squareds. I think I get negative 10x. And negative 3 minus negative 12, that's a positive 9. And you'll notice that you can't really do anything more because we'd have to get some fraction going up here, like a fraction with an x in it. And then it would no longer be a polynomial because we aren't going to do something times an x squared to get an x. So that is our remainder at the end. Right down here, that's our remainder. It almost wound up in just the right spot. So if we were to actually write our final answer, here's another way to write the division problem. This polynomial divided by this polynomial, the answer is 6x squared minus 7x plus 12. And then instead of like writing remainder, negative 10x plus 9, we write it as a fraction. If you remember, you used to write remainders as fractions sometimes. So we're going to put negative 10x plus 9 over what we were dividing by, which is kind of the standard way to write a remainder, right? Even when you're talking numbers, that's how we do it. Little trouble. Little trouble. Okay. So that right there would be our final answer. It has that kind of weird remainder, which is strange. Yeah. So that's long division. Long division's super useful when we're dividing by quadratics or cubics or anything bigger than that. But there's actually a shortcut to long division. It's called synthetic division. The catch is it only works if you're dividing by a linear divisor. You can divide by x plus 1, but you can't be dividing by any quadratics or anything of a higher degree than that. So here's an example. If we wanted to take this quadratic divided by this linear. And sort of the setup, you might remember this. Start out by kind of making a big old L shape. And we're just going to take the coefficients of the dividend, the 1, the 3, and the 5, and line them up right here, the 1, the 3, and the 5. And this might be a little weird because the thing we're dividing by, we're actually going to think of that as being an x equals negative 1, you know, because that's what would be the 0 of that factor. So you're always going to put the opposite of the number out in front. So that's the setup, and then the division begins, and the steps go like this. You drop down the leading coefficient, and then you do that times that and put it there. So negative 1 times 1 is negative 1. And then, unlike long division, we're going to add in synthetic division. So we'll do 3 plus negative 1 is 2. And then we'll repeat that kind of swinging around motion. So negative 1 times 2, put it here, and we get negative 2. And we add. So 5 plus negative 2 is 3. So our answer is 123, but not really. Like, our answer is supposed to be a polynomial. So here's how that works. Whatever you get, whatever the last number is, that's going to be your remainder. And then you just start building the polynomial out of the rest. So this is just going to be our constant, our number. The next one is going to be our x. If we had a next one, it would be our x squared and an x cubed. But in this case, we only go up to an x factor. So our final answer would be 1x plus 2, the number, with a remainder of 3. And if we wanted to write that out, we would write 1x plus the number 2, and then we're going to write our remainders the fancy way. So 3 over what we were dividing by. Something interesting is the remainder theorem. It says that if f of x, that would be the top one, is divided by an x minus k, in this case k was that negative 1, there's this really neat thing that we learn. The remainder is f of k. That might mean nothing to you, so let me show you what it means. So f of k, f of, and remember k is the negative 1. What would happen if we just took that negative 1 and we plugged it into that original function that we were dividing into? Let's try it. So we're going to do the negative 1 squared plus the 3 times negative 1 plus the 5. And we're just curious to see what we'd get. So we'd get 1 minus 3 plus 5. And it looks like the answer is 3. And that's exciting. No, really, that's exciting because did you notice that the remainder is the value of the function? I think that's awesome. And so last year you even evaluated functions using synthetic division. So that's neat. That's called the remainder theorem. If you divide a function by x minus k, then the remainder is the value of the function at that point, right? Kind of neat. Doesn't seem very useful yet, but wait, I'm going somewhere with this. Let's use that remainder theorem. So we wouldn't actually have to do the synthetic division to find out what the remainder is here. So let's find the remainder using that sort of shortcut. So remember, the sort of shortcut is that we're going to find the remainder by plugging in, and this time I guess, again, our k value is what they call it. Our k value would be the negative 1. So let's plug a negative 1 into the thing that we would divide into. So we'd have negative 1 to the 4th power minus 4. Oh, minus 1. And so that would be 1 minus 1. And we get 0. So if the remainder theorem is true, and it's a theorem, so it's probably true, that should be our remainder. Do you believe it? Let's check it. It says then check using synthetic division. So let's do our synthetic division. And this is actually a good example to do because do you know what to do when you have a 1x to the 4th, but then there's no x cubes, no x squareds, no x's? You have to put like zeros in. So here's my 1x to the 4th, my x cubed, my x squared, my x to the 1st, and then my plain old minus 1. So that would be the setup for an x to the 4th minus 1. We're dividing by x plus 1, so we'll put the number negative 1 out there. So let's do our synthetic division. Drop it down. That times that, put it here. Add. 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 Oh yeah. Our remainder is the value of the function at that point. I just think that's amazing. And what's even cooler is that a remainder of 0 is going to start to be our friend. So let's just talk about that for a minute. What does a 0 remainder tell us? Well, we know that when we plug in the number, we get 0. And that's cool, right? We have a 0. We like numbers that give us 0 for the y value. And so since we know it's a 0, we know that that's a factor, right? That's why it went in evenly. That's why the remainder was 0, because it's a factor. So we could factor up that thing to make the original function. And so this is pure gold right here, the factor theorem. A polynomial f of x has a factor of x minus k if and only if f of k equals 0, which kind of makes sense, because if it's a 0, it's a factor. You know, like roots, solutions, zeros, x-intercepts, factors, they go together. And that's the factor theorem. That's like the official, there it is. So we can, you know, check pretty quickly to see if x plus 3 would be a factor of that cubic. A couple ways we could do it, right? So we could try plugging in a negative 3, or we could do a synthetic division. Totally up to you. So two ways to do the problem. We could either plug in the negative 3 into that function, you know, which maybe is kind of a pain because those are big numbers and stuff. Or the other option is you could divide the negative 3 synthetically, but then you'd have to be careful because we'd have an x cubed, no x squared, and then a negative 19 for our x, and a negative 30 for our constant. So either way, and we should be able to find out if the remainder is, what are we looking for? Do you know what we're looking for? What are we hoping for? I totally like that a lot better, because did you see how I didn't even like, the math was like 19 times 3? Some of you can do that right in your head. I would probably screw it up, especially when I'm recording a video for you. But that was easier math for me. And I got a remainder of 0. Is that awesome? That's awesome for us now. If our remainder is 0, then we know the answer to this question. Is x plus 3 a factor? Yes. If the remainder is 0, it's a factor. So now we can factor this. So before, we only really factored cubics using that weird grouping method, but when there's only 3 terms, you can't do that. But now we have like a factoring technique, right? We know that one of our factors is x plus 3. And obviously there's some other factors going on here. And actually, would you believe that our answer right here is the other piece, right? So x squared minus 3x minus 10 is the other piece, because we took this and we divided it by x plus 3, and we got x squared minus 3x plus 10, minus 10. And so this is equal to this times this. Well, this isn't factored all the way, so we could do one step better and have a nice final factored form. That look right. And so that's kind of what I expected to see. I expected to see an x to the 3rd going on, right? And so it turns out that we can now factor complicated cubic functions just by being able to pick out one factor that works. I want to talk to you about something called repeated division. I'm not sure if you ever did this in Algebra 2, so if you've fallen asleep, now's the time to wake back up. And I'm going to let you cheat just a little bit on this, because I'm going to let you use your calculator to make a graph. Making the graph is going to help us on this. So again, if I asked you to factor this, holy cow, like, how would you even group that? We don't know any ways to do that unless we kind of use this new idea of the synthetic division giving us the factors. So, if you can look at this graph, I have a couple of hunches about what zeros might be. Like, do you see this one? I feel like x equals 2 might be a 0. Therefore, x minus 2 will probably be a factor. And so what I'm going to do is I'm going to set up this giant synthetic division, which is actually fun. Once you get good at it, it's really fun. So here we go. And it's a 1x to the 5th, a 2x to the 4th, negative 4, negative 4, negative 5, negative 6. And I don't think I had to put any placeholders in there, so I'm good. And I'm just going to quick do my synthetic division, so drop it down. I'll shut up because I usually make more mistakes when I try to talk. Oh, yeah. I got 0. That means that truly was crossing through at 2. It didn't just look like it, it really was. I just proved it because it gave me a 0. So the point 2, 0 is on the graph. Bam. So now I've kind of brought it down to, I know I have a factor of x minus 2. I know I have a factor of whatever, I guess, x to the 4th plus 4x cubed plus blah, 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 blah. But now here's where the repeated idea comes in. I'm going to take my answer, because I know I could probably break that guy down a little more. And so then I go back to my graph. I look at, well, doesn't it look like maybe negative 1 is another 0? And we'll try it. What's the worst thing that could happen? So we'll try a negative 1, see if that works. Oh, yeah. It does. It works. So that truly is crossing right through at -1. I'm betting you that I could divide. What are you thinking? See that -3? Let's try it. So again, we don't go all the way back to the beginning. It's called repeated division because I want to take it out of the leftovers every time because I'm trying to reduce this baby down. So I'm going to try that -3 now. What do we say? Oh, yeah. So again, that was a winner. The point -30 is on the function. And now we still have some stuff left over, which is kind of strange. And what does this stuff represent? A remainder of 0. There's my number. There's my x. There's my x squared. So I guess what's left over is a 1x squared plus 1. What's that all about? Well, there's not really a way to factor that anymore, actually. There's nothing we could plug in for x that would make that equal to 0. So I think we're done. And let's write out our final answer. So here's the final answer. If we wanted to factor this monster, it'd be all about x minus 2, x plus 1, x plus 3, and x squared plus 1. Which, if that was x squared minus 1, we could factor it some more, but x squared plus 1 doesn't factor down anymore. And if you thought about foiling this out, I wouldn't recommend it, but if you thought about foiling it out, you would get an x to the 5th, which kind of verifies that this would have exactly the same graph as this, and this is just the factored form. I'd like you to try this one, so I'm going to have the teacher pause the video, and I want you to see if you can factor this all the way. Now I'm assuming you paused and you tried, so now I'm going to try and see if I get the same thing you did. I think I'll try that 1 right there. Yep. Now here's something that I kind of gave you that hint. I told you to look at the even and odd multiplicity. Did you notice how this guy just bounced off? That tells me that that's probably a double root right there. What that means is I could probably, you might not have done it in this order, but I could probably divide out a second factor of x minus 1 because I saw that multiplicity looking like it was a double root. So let's try it. She was right. So then I can try dividing out the -2. Again, it doesn't matter what order you do this in. We'll all get the same answer at the end. And now honestly, right here, this is x plus 3. So I know that -3 is going to come out. I mean, you could do it just for fun. And who wouldn't want to do? Okay, so we'll take that -3, and it should come right out of there. And this 1 that's left over, you know, if we throw that in, it's just like multiplying by 1, so it really doesn't mean much of anything. So here's what I was hoping you'd get for your final answer. You'd have a couple of those x minus 1 factors, right? An x plus 2, and an x plus 3. I always like to double check and just think about imaginary foiling this out, and if I were to foil this out, I feel like it would come out with an x to the 4th as the leading term, which is good news, and so I'd say that looks pretty legit. And we had the double root and the 2 single roots that just crossed right through, right? Awesome. All right. So just to make sure that you learned something, here's what I was hoping you'd get out of this lesson. The remainder of 0 when you divide by a number, and the factor and the function equaling 0, those all go together. And you sort of knew that before, right? Like, you know, y values of 0, right? X-intercepts, zeros, roots. They have no remainder because they divide out evenly. They make factors. All of those go together, and that's what those big theorems were about today. And this is just that example that we did earlier. If you had an f of x, and dividing out a -3 gives you a 0, and that implies that x plus 3 is a factor, and that means when we plug in a -3 we get a 0, and those things always go together. That's just kind of the idea. So we love it when we get 0 remainders, because we know we've found factors, and it helps us to factor. Your job is to try these problems. It looks like a giant list, and I think I have a typo up there. That must be a 68, huh? I'll double check, but that looks right. Yeah, that's better. So that would be your assignment. I want you to have it done for tomorrow, and I will be here. And you can ask me questions then. Again, if you'd like to see this video again, I'm going to put it on SharePoint. That way you can go back and check out anything I did too fast. So thanks, guys. Get to work. Help each other. See ya.